Welcome everyone to this first January 2024, First Fridays. And we're very glad to have Professor Jim Woodhouse back with us to discuss the properties of wood. So Jim?
Okay, thank you, Fan. So, share screen, do it, and do it. Okay, you should be seeing slides. So, there won't be any path-breaking, cutting-edge research in here. It's a kind of summary of various things to do with wood. A bit of picture book stuff about the cell structure, a bit about stiffnesses and damping, a bit about measuring, and a little bit about criteria, mainly a warning. So, well, you'll recognize this. Everything I'm going to say can be found in euphonics, I think, pretty much. So here's the kind of thing you're used to seeing. So start at the beginning. We need a little bit of botany. So there are two kinds of trees, and this picture happened to have them both in. Now, sometimes called softwoods and hardwoods, but that's really quite a confusing name, because you need to remember that on the botanical definition, balsa is a hardwood and yew is a softwood. And the difference between the two things is not really to do with hardness of the wood. It goes surprisingly deep into evolutionary history. So the whole plant kingdom is divided into two things. And the defining characteristic is what you see if you watch a seed sprout. So some things like grass put out a first shoot that's a single spike. A lot of things like mustard and cress put up a pair of little leaves as their first thing. So those first little leaves are called cotyledons. And so there are monocotyledons and dicotyledons. That's not a word we're going to need to use again in this talk. But the two line separated softwoods, conifers, are monocots, hardwoods are dicots. And the fact that both kind of look like trees is probably an example of convergent evolution, because the lineages of the two types goes back a really very long time. I'll be nearly all the time talking about softwoods or about generic things. Spruce and the like. And that's good news from the botanical point of view, because they're simpler. So these softwoods, spruce, pine, and so on, are coniferous trees. They don't make flowers, they make cones. And they have a really simple structure, which is good news. And here's a little picture. So here's a schematic. You can recognize this as a kind of sawn off tree. And we can define three directions in the tree, and I'll keep on using these, so you need to note this. So we've got the L direction, longitudinal, up and down the tree trunk, the R direction, radial in the tree, and the T direction, tangential to the annual rings or to the bark. So L, T, and R. Here's a scanning electron micrograph in the same orientation, more or less, of a typical piece of instrument quality spruce. And we're starting to see the cell structure, and I'll talk about this and show some more pictures. Probably the first, well, what do we see here? We see a lot of empty space. We see thin-walled cells here, suddenly turning into rather thick-walled cells here. That is the edge of one of the annual rings. Now my R arrow here is pointing outwards in the tree, in the direction that the tree grows. So what happened in the year when this annual ring grew is that the tree had been dormant through the winter, and then when the magic moment came in the spring and it started growing new cells, it leaps into life with large thin-walled cells. and each one grows another one next to it as the tree gets a little bit bigger. And if we skip to this previous annual ring here, as the season comes to an end, the cells continue reproducing, but the walls get thicker and the space inside gets smaller, and it ends up with rather solid stuff. And then the tree decides to pack up for the season and stop doing it. And that's what makes your annual ring structure. So basically the structure of a softwood like spruce is the best thing to think of is a box of drinking straws. They're long tubes aligned vertically in the tree. They've got thin walls and a lot of empty space inside them. And these long tubes are called tracheids. That's the main kind of cell. So most of the substance of a spruce or any other softwood is made up of these long tubes called tracheids. I'm not really going to say anything about chemistry here, but the main constituents of wood are three things: cellulose, hemicellulose, and lignin. The cell walls have got complicated microstructure. They've got helical windings and all sorts of stuff, which we needn't go into. Adjacent cells are glued together with something amorphous, and that layer in between is called the middle lamella. And now here are some views of end grain spruce. And if you look at this most magnified one, you can see the middle lamella here. If you can see my pointer, there's a small gap here. You can see something different happens. So this cell here has got windings going round and round its wall. The one next to it has also got windings. They're glued together with different stuff. If what you do with your spruce is make paper, which is probably not what most of you do, then the trick for paper making is to dissolve the middle lamella without destroying the tracheids. So the fibers that end up making your sheet of paper or your cardboard is made of a mat of individual tracheids that glue together in some way. So here's a least magnified view of end grain. So we were in the RT plane. This is, remember, radial outwards. And here's one complete annual ring. Someone needs to mute. And this is the tangential direction. And these are just some more pretty pictures. These are long tubes. You can peer into this empty space. Here's a different view. This is the view you'd see on the surface of a soundboard. This is the longitudinal radial plane, more or less. So what you're seeing here is all the tracheids who've had their lids taken off by the plane or the knife. So you're seeing these tubes running here, and it's not quite exactly following the grain. So this tube here is diving in underneath the next layer, and this is the next layer of tracheids above it. Now you can see some other things in this picture. There is one other type of cell in softwoods, and these are called rays. And all these crosswise things here are rays. You can see there's one here, there's one group here, there's one group here, there's another one up here. So these are cells that are running radially in the tree. And they don't contribute very much of the substance or very much of the strength. I think they're really important to the internal economy of the growing tree, because they can transport fluids in the radial direction. Now we can see some other details in this picture. So the tracheids can communicate with each other. I've said they're long tubes like straws. Of course, they're not infinitely long. They don't run the whole height of the tree. They taper down to a point eventually, and then the pointy ends of the next lot kind of interlock with them. So each tracheid is a sealed unit, but that's no good for the tree. They need to be able to communicate fluids. So they have these little things that look like donuts or bagels here. They're called bordered pits, and those are little pores that link the tracheid to the one next door. At least they link them when the tree is living. When the tree dies and then the wood dries out, each of these bordered pits has a little valve in it, which usually welds itself shut against one face or the other. They have an important role. When the tree's alive, they do act as valves so they can let the flow through or stop it. In dried wood, these things all close up, and that's why spruce floats when it's dry. It's not easy to get liquids inside it. It will continue to float for quite a long time because there are pores linking the cells, but they're closed. There's one more kind of pits. Now here's a slightly closer. Now you recognize the landscape now. We've got tracheids running vertical. Here's a ray running across horizontally. And you can see these smaller little oval openings here. Those are called piscioid pits. And they let fluids link between the tracheids and the rays. So stuff can be transported in the radial direction in the tree. So that's about it for the botanical structures of softwoods. Just two types of cells and two types of pits linking them up. Everything else is variations on that theme. Here's another view of some tracheids diving down here like subway tunnels. Here's a ray running across the surface. And if you look in the bottom left, you can see there's another ray just underneath this tracheid because we can see lumps and bumps on the bottom and some of these piscioid pits where it can talk to these tracheids. And here you can see the middle lamella coming slightly unstuck, probably because of my knife cut. Here's a different plane. Now this is the longitudinal transverse tangential plane. This is the plane you'd get if you do a cross section through the thickness of a soundboard, if it's perfectly quartered. Not so structured. It all looks rather random. You can still see tracheid tunnels diving off here. And you can see a lot of these sort of things, rows of little black dots. And that's an array seen end on. So each of those rays is a stack of maybe a dozen cells stacked up vertically, running in the radial direction, which is perpendicular to this plot. And say not in fact contributing very much to the mechanical properties. Now here's an interesting one. This is a piece of spruce which had been nipped up in a vise a little bit too tightly for its own good. It's a piece of wood that was serving as a buffer in the vice jaws, and then we thought it would be interesting to see what it had done. And you can see what's happened here. There's a row of a couple of cells. And under the pressure of the vice, which is left to right in this picture, these cells have collapsed by buckling and they've all squidged up sideways. Not something you'd want to see in the middle of a soundboard, but it is something that you're doing. This is a view of, so this is the end grain of spruce, and then there's a right angle corner here, and here's the surface running away from you. And that surface has been scraped with a cabinet scraper. And you can see that that's done two things. First of all, the surface looks quite smeary and flat. So the stuff of the wood cells has been smeared out a bit by the scraping action. So this is not a clean cut. It's done some burnishing. But if you look below the surface, the first 2 or 3 layers of these thin-walled spring growth cells here have collapsed in rather the same way that we saw in the previous picture. The hard bit on the annual ring, on the other hand, has been cut fairly cleanly by the scraper. There isn't enough empty space here to collapse the cells. So the hard material has been cut, but the softer stuff just after the annual ring has been collapsed. Now, you know what happens to wood like that if you moisten it and then wait for a little bit. You raise the grain in woodworking speak. Here's a picture of roughly the same view after the grain has been raised, after the wood has been moistened. And you can see what's happened. The two rows of cells that had been squashed by the scraper have more or less popped back up again into their original shape. But on the hard bit of the annual ring, there wasn't any collapsed stuff. There, the scraper had cut it quite cleanly. And the result is a little step as you go through the annual ring, and that's why the grain is raised when you moisten something where it feels grainy and like corduroy. This is the only picture I'm going to show of maple. It's a hardwood. Hardwoods are more complicated. There are several different cell types. I'm not going to talk about them. You can see that on it's still got tubes running into the surface. The walls are thicker, it's more dense. And it's also got these very large vessels. That's characteristic of all hardwoods, that they have these larger vessels in them. But I'm not going to say anything more about that. So let's start talking about the mechanical properties of wood. And we'll start with stiffness, and mostly I'll talk about stiffness. So here's my schematic of a tree again, just to keep reminding you of the directions. So the way to understand stiffness, perhaps, is to think about cutting a little rod-like sample out of your tree in one orientation or another. So uniform cross-section, I've drawn it square, but it actually wouldn't matter for the purpose of what I'm going to say, what if it be a circular section, for example. Now we can do three potential, so kind of thought experiments. This is not necessarily the best way actually to do the measurement, but it's a good way to visualize it. So if you take this rod, if you grab hold of the ends and you pull, then you can measure how far it stretches. That measures the stiffness along the orientation of the rod, and that stiffness is characterized by something called Young's modulus. It's much the same as you do with a wire. If you stretch it, it governs how sensitive the tuning pegs are when you tune a string, because you're stretching the string as you pull it up to pitch. Less obviously, but nevertheless true, it's this Young's modulus, this stretching behavior, also governs the stiffness in bending. When you bend something like this, then on one side of it you're stretching the fibers, and on the other side you're compressing them. But both the stretching and compressing are governed by Young's modulus, so the stiffness to bending is governed by the same thing. Now, that's not the only thing we could do with our rod sample. During the same experiment, while we're stretching it, if we wanted to, we could measure the width and the height across the cross-section. And what you would usually see is that as you stretch it lengthwise, it pinches in a little bit in the cross-sectional direction. And the ratio of those, the pinching in divided by the stretch, is something called Poisson's ratio. And it's medium important, I suppose. There's a third thing that we could do with this rod sample. We grab hold of the ends, but this time, instead of stretching it, we try to twist it along the length. We apply a torque between the two ends, and we can see how far it twists. And that's governed by a different kind of stiffness, known as the shear modulus, because each individual layer of the rod is trying to shear relative to the next layer. So the twist that you build up along the length is made up out of shear. But the fact that shear modulus governs twisting is a thing we'll come back to shortly. Okay, so those, given one rod, we could do three experiments and measure three things. And for solid wood, as is kind of obvious with these three directions, we've already seen that the wood structure is quite different in those three directions. So we could cut three different rods, oriented those different ways, and we could do this experiment with all of them. So we measure three things for each rod. We got three rods. So for this solid wood, we get a total of 9. And there's a little bit of mathematics in the background. I won't be showing any mathematics here, but that says that that's the whole story. complicated enough, but a solid wood, if you ignore the curvature and knots and all the other complicated things that happen in real wood, you need 9 stiffnesses in a generic sense. They aren't all so, but some of them are more important to you than others. If you had just had a thin flat plate like a guitar soundboard, then there's another little bit of maths that says that now you only need 4 of these stiffnesses only. And one of those 4 is very rarely important. So there are 3 important ones, and we'll see what those are shortly. So we start with 9 for the solid wood. We cut a flat plate out of it, and we need 4. And most of the time we can get away without thinking about one of those. So how do we measure those? Well, one way is to use the kind of little bar samples that I was talking about. So here are some spruce rectangular beams cut out of the offcuts from a set of violin tops. And we can see several things in this, but for the moment, how can we use this to measure the stiffness? Well, I said we could stretch it and measure how much it stretches. That's actually a relatively difficult thing to do. There's a much easier thing to do, which is to measure the bending frequency. So the lowest vibration mode of one of these little bars, this is an exaggerated scale, of course, but it vibrates just like the lowest mode of a xylophone bar. And there is a formula. I'm not going to show it to you, but you can find it in Euphonics if you want to see it, where if you measure the dimensions of the bar, length, width, and height, and you weigh it, and then you measure the frequency of this vibration mode, you can back out of that the Young's modulus along the orientation of the rod. As I said, that Young's modulus governs bending. Here's how you might do that. This is my favorite way to do that measurement. Here is one of those spruce samples. So this is just a piece of U-channel, 2 rubber bands so that you can move them around, and you slide them up and down so they're roughly under the 1/4 and 3/4 points, which are the nodal points of this vibration mode. You tap it with a pencil, put a little microphone underneath, grab that into your FFT analyzer, and with a bit of luck, you'll see a clear peak going with this lowest vibration mode. There'll be other peaks going with other vibration modes, but just that lowest one, and a formula that I'm not going to show you here, would allow you to deduce the Young's modulus. If you're the proud owner of a Lukimeter, then so that you measure the speed of sound through something like this, then if you combine that with the density of the material, you can also back out Young's modulus. So that's one way to measure vibration. That's all very well. Well, let me just go back one. That's all very well, but that gives us one stiffness. It's a nice, clean, simple measurement. We have a beam cut in some particular orientation. We measure one frequency, and it determines the Young's modulus along the orientation of the beam. So we could cut beams in different orientations and measure one thing from each of them. But I said there should be 9, so that isn't enough. Now, if you're a guitar maker rather than a violin maker, you're in a better position here, because the wood that you buy from the wood dealer, well, these are spruce plates that I've cut to a square shape, but any rectangular shape would do for the thing I'm about to describe. And a constant thickness rectangular flat plate is usually what the wood dealer sells you. So a guitar maker can do something without needing offcuts, just using the blank. And there are 3 vibration modes of a plate like this. I've shown them as Chladni patterns in the top row, and we've got little animations of what the vibration looks like for those modes. So this one, it's usually the lowest frequency, and the plate is twisting. It's what you do when you twist the plate in your fingers if you're feeling the twisting stiffness. And this one has got cross grain bending and this one has got long grain bending. And the same thing is true that I just said for the beam. If you measure the dimensions of your plate, the two in-plane dimensions and the thickness, and you weigh it, and then you measure the frequencies of these three vibration modes, then you can back out three stiffnesses. And remember, I said that for a flat plate like this, there are technically four stiffnesses, but only three of them are really important. And these are the ones. So you can get everything that matters to a first approximation for a guitar maker, for example, by doing this experiment on these rectangular plates. Not so easy with a tapered violin blank, so too bad. Now then, this plate here was a quite nice quarter cut plate with the split direction running this way, and you can't see the annual rings here, but running nice and perpendicularly through the thickness. But that's not always what they sell you, is it? Maybe the timber yard has cut the guitar top plate like this. It's a little sketch here. So it's nicely capturing the L direction, but it's not really lying in the quarter cut direction. The annual rings are not perpendicular to the surface, they're going through at some angle. Well, that makes a big difference to these effective stiffnesses of that guitar top. There are still, whatever the ring angle, so this is a graph as a function of the ring angle in degrees, where 0 means the perfect quarter cut plate. And by the time you went all the way up to 90 degrees, it would be a pure slab cut plate, tangential. They'll never sell you one like that, perhaps. But they may sell you things in the middle here. Now then, there are three curves here because there are these three stiffnesses. We've got the long grain stiffness, we've got the twisting stiffness, and the cross grain stiffness. And what you can see is that the long grain stiffness and the twisting stiffness don't very much care how the piece of wood has been cut out of the tree. But the cross grain stiffness really, really does care about it. Now, I've plotted these stiffnesses on a logarithmic scale here. So there's a factor of 100, a factor of 10 here, and another factor of 10 here. So there's more than a factor of 100 in stiffness covered by the whole axis. The cross grain stiffness, which is the one that's the blue curve here, that's sensitive to the ring angle, by the time you're 10 degrees off the quarter, you've lost approximately a factor of 2. And if you go all the way to 45 degrees, you've lost almost a factor of 10. So an order of magnitude less stiff. Now, who would ever try to sell you something like that? Well, they do. Here is a spruce plate sold. Bernard Richardson gave me this. He's a guitar maker in his spare time. This was sold as suitable for making guitars. And this has got rings going through pretty much at 45 degrees. So it's right at this lowest stage here. And if I just quit the share for a moment, stop share. No, I need to quit the PowerPoint. That should mean you can see me. And here is, where's the camera? Here is that spruce plate. You can't see on this view, but it's the same one. So the long grain direction, it feels just like spruce. It's quite thin, but it's very stiff. In the cross grain direction, it is scarily bendy. This plate has been passed around a number of lecture rooms, and I'm always terrified that the undergraduates are going to snap it because it's so tempting to bend this a lot. Usually, that's not what you want. 45 degree stuff. Now, let's have to share back and do it and show the slides. Well, that graph has a companion. which is the influence of grain angle rather than ring angle. So if you're not quite in the split direction, so the wood fibers are not absolutely parallel to your plate, but running through it at an angle, then that will be the grain angle. And again, degrees, naught means perfect split. By the time you get to 90, it's at right angles to the tree's axis. Again, we got three curves for the same three things: cross grain stiffness, long grain stiffness, and twisting stiffness. And this time we see that what you'd expect, it's the long grain stiffness that's really, really sensitive to this. Well, of course it is, because you've no longer got the, as soon as you're away from the split direction, you're avoiding the stiffest direction of the wood. And again, by the time you went all the way down here, you've lost more than a factor of 10. This dotted line here, again, is on the 10-degree line. And as it happens, 10 degrees off the grain is enough to lose you a factor of 2 in long grain stiffness. The cross grain stiffness doesn't vary all that much. The twisting stiffness is quite sensitive to that. That also goes down by a big factor. Now, you may say, but I'm always very careful to get wood that's exactly on the split. Well, that is true, but unless you're an acolyte of Bill Fulton, you probably carve arched plates out of the solid wood. If you bend your wood so that the wood fibers lie in the arch all the way, then you maximize this stiffness. By the time you've carved an arch through this, then on the falling slopes of the arch, you can easily get 10 degrees and more. And so it might matter for the details of the vibration behavior that the local stiffness on the slopes of the arch may be significantly lower than it is in the middle of the plate, where you're nicely aligned along the split direction. Right, so why is wood so stiff along the grain direction? Well, there's a simple way to visualize this. Remember those drinking straws? I said that any softwood like spruce more or less has this structure, these long, thin-walled tubes. So if you take your box of drinking straws and you apply a force along the length of the straws, it's pretty stiff, because the tube walls, in order for the whole thing to get squashed by you pressing it there, all the tube walls would actually have to compress. But in the crosswise direction, if you squeeze your box of straws crosswise, you can squash it flat quite easily. You know, you stand on a box of straws from the side and the whole thing will squash flat. So here's a kind of schematic of the cross grain structure of wood. We saw all those micrographs earlier. And if you apply a force in that direction, in the R direction, as I've shown it here, then the wood can squash in that direction by bending the walls. Each of these zigzag walls along here can go into a slight S shape, the thing that we saw in a large way when I showed those cells that had buckled. And again, I'm just going to quit the share and quit the PowerPoint for a moment so you can see me. I have a test object here. Where's the camera? Now, this is a little bit of honeycomb structure, and it's made of silicone rubber. There's a reason for this that I needn't go into, but roughly speaking, this looks like a very small piece of spruce. Now, in the L direction, I can squash it this way, and even though it's made of very soft rubber, it's pretty stiff in this direction. But in the cross direction, I can stretch it and compress it just in my fingers very easily. And if you can see those cell walls, can you see the bending taking place? So it's soft in this direction because it only needs to bend. It's stiff in this direction because the stuff has to compress. Okay. Back to the share. Back to the slides. Now, this has a consequence, which is interesting. Now, all trees, the solid wood of all trees, is made of roughly the same stuff. There are small variations, but the cellulose, hemicellulose, lignin, it's the same kind of material. So this stretching versus bending comparison tells us something rather curious, which is that now the long grain stiffness, so when I squashed it along the grain, every single tube wall was having to squash. So, and of course the density is proportional. If the stuff is always the same, the density of the wood is proportional to the total cross-sectional area in this plane. So the long grain stiff, which is also, the stiffness is also proportional to that total cross-section area. So the prediction is that the long grain stiffness should be more or less proportional to the density. But in the cross grain direction, for reasons that I won't quite go into, although I'm sure some of you will know, remember that when we squash in the cross direction, we are deforming it by bending those walls, and bending stiffness of a little beam, like one of these cell walls, varies like the beam thickness cubed, not linear, but the cube of it. And so the cross grain stiffness is proportional to the cube of the typical wall thickness, and the typical wall thickness is proportional to the density. So the prediction is that cross grain stiffness should be more or less proportional to the cube of density. And because all wood is made of roughly the same stuff, then in a broad brush sense, this applies across every different kind of timber. Unlikely, but true. Here's some data. I'll come back to this plot a little bit later on, but this is a plot of density along the bottom on a logarithmic scale for technical reasons, and Young's modulus up here, again on a logarithmic scale. This blue blob here is data, so each individual piece of wood would be a dot in this diagram. It would have a certain density, and this blue island is the long grain stiffness. The green one is the cross grain stiffness for perfectly quarter cut specimen. So you take a single tree, single sample of wood, it has one density, one value of long grain stiffness, so a dot up here somewhere, and also one value of cross grain stiffness, so a dot down here somewhere. Now here's just a data collected from a database of lots of different kinds of wood, long grain stiffness and cross grain stiffness, all joined up by this kind of blob here. Well, the predictions that I just made on the previous slide turn into these two red lines here. We predicted that the long grain stiffness should, broadly speaking, be proportional to density, which means that on this log-log plot, they should all lie along a straight line with a slope of 1. And if you count squares here, this red line goes through 50 at a modulus of 1. And by the time it's gone up by a factor of 10, it's going through this junction, which is at 500. So it's 10 times the density and 10 times the stiffness, so a slope of 1. The prediction was that the cross grain stiffness should go broadly like the cube of density. And the same argument on this log scale says that we should get a straight line with a slope of 3. Which is this red line here. Well, we lose it at the very end. This is balsa, that's, as you know, a very extreme material. But the general trend of this curve is really surprisingly close to this prediction. So in a very broad sense, long grain stiffness proportional to density, cross grain stiffness proportional to the cube of density. Holds up pretty well. We'll see this diagram again in a moment. Let me say a little bit about choosing wood. Now, maybe some of you do this. There's a lot of people use this index of merit for wood, sometimes called the radiation ratio. Now, I'm not going to do the mathematical derivation of where this condition comes from, but I'm quite sure that a lot of you have heard of this. So you can either take the speed of sound divided by the density, or you can take the Young's modulus divided by the density cubed, and then if you really want the same number, you take the square root of that. And a lot of people believe that maximizing that gives you the best wood. So low density, high stiffness, a large value is good. Well, as with many things, that's true up to a point, but it's, I'm going to give you a note of caution about that for the moment. But first of all, let's just believe this for the moment and go back to these material property graphs that we had a couple of slides back. Now, let's start with this one on the right, because that's the one we've seen before. This prediction, if you're trying to maximize Young's modulus divided by density cubed, then that also translates into a straight line on this log-log scale. And it's actually the same straight line that we just had for the cross-grain stiffness. It's a slope of 3. That is to say, right, all points lying along this red line here, for example, should have exactly the same value of this radiation ratio or index of merit. If you want to maximize that, you want to push the line as far to the left as you can go. Pushing it to the right means higher density for the same stiffness, so less good. Pushing it to the left means lower density for the same stiffness, so better. So roughly speaking, you want to, if you believe this criterion, I'll come back to that in a moment, the very best wood or material in general is the last one you get as you push this line as far that way as you can go. And what's the very last thing you go through? The very last thing is balsa. Did I see Doug Martin on the participants list? So some of you will know you can indeed make violins with balsa. You have to be rather careful with other aspects of the engineering, but they work a lot better than you might have guessed. Usually that's not quite what you choose. Usually you choose something in the spruces line, which is a bit further up here. But just look for a moment at this left-hand version. Now this is exactly the same diagram, except that this is all, in some sense, all engineering materials, not just wood. So it's got 2 islands for wood parallel to the grain and wood perpendicular to the grain, which are the ones we've got in the right-hand diagram, but it also shows you all the other kinds of materials. So this kind of blobby triangular shape here is all the metals. This vertical blob is all the polymers. This one here is our composite materials, carbon fiber, glass fiber, reinforced. This one right at the top here are ceramic materials. So there are engineering ceramics like alumina and silicon carbide, which you might have in your drill bits when you're putting shelves up. And right at the very top, you get diamond. That's the highest stiffness of any known material and a particular density. So here is every possible material. Here's the same red line, which we remember, if we're choosing a material to make a violin out of, we want to push that line as far as we go. And this is the diagram that perhaps tells you why you still make violins mostly out of wood, because based on this criterion, it's the very last material you pass by. The next best is the tip of this blob here for the composites, which is the high performance carbon fiber composites. Well, some people do make musical instruments out of carbon fiber sandwich structures, and they can be okay. You don't make instruments out of solid metal of any kind. All the metals are way behind this line for the position for the woods. Some metals will be less bad than others. The very worst might be lead. That's plausible enough. Things like titanium are further in the good direction. So if you were making a metal violin, you might want something light and low density, magnesium or titanium, the same kind of requirements that if you're building an airplane or a spaceship. Polymers are also not very good. What this diagram doesn't have in very large extent, but they're disappearing off the bottom here, are polymer foams. So this blob that's disappearing off the bottom end of the graph shows all the properties you can make by taking these polymers and making foams of various different kinds. And you can see this blob actually getting fairly close to the red line here. But it has really low density foams, have other difficulties if you were trying to carve a violin out of them, perhaps. So back to this criterion, I've already implied that I'm going to cast some doubt on this. Not in the sense that it's never useful, but it's really, really important to use it with care and to remember how this criterion is derived. And I dare say not very many of you do remember the little bit of mathematics behind this. Now, this criterion is derived by making two assumptions. One is that your design aim when choosing a material for your violin is to make it louder. Just that, nothing else, no subtlety. You want something which for a given stringing and a given resonant frequencies makes the loudest possible sound. Well, maybe that is what you do, and maybe it isn't. The second assumption is that if you made violins out of different material, you would essentially do plate tuning. You would adjust the thickness of each material in order to keep the resonant frequencies of the plates exactly the same. So stiffer stiffer materials will need thinner plates. Heavier materials will need thinner plates for a different reason. It's by putting those two assumptions together that you get this radiation ratio criterion. Maybe you do want to make loud instruments, but do you necessarily adjust the thickness to keep the frequencies exactly the same? There might be other considerations that govern your graduation pattern. In particular, if you kept the same graduation pattern, if you use different materials but the same thickness pattern, then you could go through the same little piece of mathematics, but you would get a different answer. There will be a criterion involving Young's modulus and density, but it won't be this one. It won't be Young's modulus over density cubed. So if you don't follow both of these assumptions here, then this criterion in its strict sense will not be true. I'm not saying the criterion is not useful under any circumstances, because roughly speaking, you know, people do quite like to make loud instruments, and probably you do make your stiffer plates a little thinner. And so you will go in the direction of satisfying both of these approximations. And that means that this criterion will give you a guideline for wood selection, but not a guideline that works to two significant figures. You know, if you're choosing between very similar pieces of wood, so you've got rather small differences in this criterion, then you would want to be very careful about whether you're really at that level of accuracy of the difference between those pieces of wood. Are you going to adjust the thicknesses in this particular way to keep the frequencies the same? So it's a useful thing, but it can be misleading. Final technical topic in this talk. I've talked about stiffness. What about damping? Damping is also important. And I'm just going to give you the short answer to that and not go into this in any great detail. But each of those stiffnesses that I talked about earlier has associated with it a measure of damping. And that's because each of the types of motion, cross-grain bending, long grain bending, twisting, well, there is energy dissipation associated with each of those types of motion. And in fact, it turns out that you can add those all up to get the total damping. So each of the stiffnesses has an associated damping factor, which means the numbers we saw earlier work for damping as well. So for solid wood, it had 9 stiffnesses, and there are 9 damping factors. For a thin plate, there are 4, 3 of them important, 1 of them not very important, and that is also true for damping. If you're keen, you can use exactly the same measurements that I described earlier using beams or plates. And this is where you do need to be doing vibration measurements rather than using your Lukimeter. But if you measure those resonances of your beam or your guitar top plate, if as well as measuring the frequency, you measure the Q factor or the damping of that resonance, then there's another formula that you can find in euphonics. Is that true? You can find somewhere. Ask me if you want to do this. And as well as backing out the stiffnesses from those frequencies, you can back out the associated damping factors associated with those stiffnesses. So in principle, it's straightforward. It's measuring damping is always much more difficult than measuring frequencies to get stiffness. But different timbers do differ in their damping properties, and that will be one of the criteria that will make a difference between different choices of wood. And this is pretty much where I'm going to get to. So summary of what I've said is that you have a perfect piece of wood, and what I mean by perfect is no knots, no warbles, and not really, I haven't really said anything about the curvature of the tree. So wood from a very large tree with no irregularities. Then to characterize the mechanical properties of that, sufficient to design the vibration of your violin top or violin back, you need the density. You need these 9 stiffnesses, 3 of those being the most important. Associated with those, there are 9 damping factors, and the same 3 of those are the most important. So as a minimum characterization, you need 1 density, 3 stiffnesses, and 3 damping factors. All of those you could measure using that rectangular plate measurement. 2 of the stiffnesses and 2 of the dampings you could measure with beam samples, but you don't so easily get the twisting stiffness from that. And that's the end of my story. So wood is a wonderful material, but rather complicated, a fact which you already knew, I suspect. And if you want to see any more detail on this or just see it again, you'll find it all somewhere in euphonics. It certainly will give you the formulae that you can use from those beam and plate measurements to back out stiffnesses. And that's it. Thank you very much.
All right. Thank you very much, Jim.
Let me stop sharing for the moment.
If you have questions, if you could use the raise hands functions, which is in the reactions, icon on the bottom of your screen. Or if you can't find it, you can always just type something into the chat and we'll get to you. So let's see, Chris.
I see the usual suspects, yes.
That was really cool. Thanks. I was wondering, one of your plots, you were looking at the grain angle versus whether you were doing a cross or inline measurement, right? But the cross at 90 degrees should be the same as the inline at 0 degrees, shouldn't it? Or am I misunderstanding?
Yes, it's one of those. Whether it's I mean, there are two different cross grain directions: the R direction and the T direction. I was a little vague about which one of those I was in. So yeah, yes, the 90-degree one is either the radial direction or the tangential direction, depending on which graph I inserted. So yes, that's why the stiffness in that direction got so very low, more than a factor of 10 down, because that is the typical ratio of long grain stiffness to cross grain stiffness. So you'd never go that far, but you can easily do, say, you can easily do 10 or 15 degrees in your arching, and maybe a couple of degrees in what the wood dealer sells you.
Thanks.
All right, Jim?
Yes, I just wanted to take exception to one thing that you said, which is that the medullary rays are not very important structurally. I think they're extremely important structurally. They are the reason that wood shrinks and swells half as much in the radial direction as in the tangential direction, and also part of the reason that the wood is much stiffer. A radial cut wood is stiffer in bending than a slab cut piece. So they're very important.
Yeah, no, you're right. I wasn't thinking about shrinkage. You're 100% correct on that. You know, I was thinking of stiffness and damping. As it turns out, for Norway spruce, the stuff you usually want, the rays are sufficiently sparse and sufficiently thin that they don't contribute very much to the cross grain stiffness. In fact, when you do the sums, some softwoods have a higher density of rays, and it plays a more significant factor. But I'm sure you're right about the shrinking
that we're looking for. Makers call it silking, but they're actually choosing for a higher density of rays when they're looking for that.
Yeah,
you see the rays on the radial surface.
I think you're right, but if that's really what you want, that tells you whether you've got the cutting angle nicely precise.
Yes.
Higher density of rays, you do better to use a different wood, actually, because some softwoods are
well, I mean, within the same species.
Yeah. No, I wouldn't disagree with any of that. Looks like Joseph.
Yes, thank you, Jim. First, let me say that's like the best and most useful talk on wood I've ever seen. So, and I learned some interesting things, especially this notion that as the density goes down, the relative stiffness across the grain goes down drastically. Now, with your assumption that, let's say, you want to make the loudest instrument, and presumably loudness relies on, in some measure, on stiffness in two directions,
Yes.
across and along, therefore, because all the modes are doing that. So within a given species, is there an optimal stiffness where the lines kind of cross? And I would love to see that diagram.
Okay, now let me bring the share back for a moment and show something I didn't say about one of the slides. Now then, is it that one? Yes. Now, so did you notice this dashed line here? I didn't mention it because the story was complicated enough already, but yeah, you're absolutely right. It's another twist to that radiation ratio criterion. You absolutely, what you say is correct, that you maybe you're interested, nearly all the mode frequencies are influenced by both the long grain and the cross grain stiffness, and maybe you want some mixture of them. There is a simple version that you can still calculate where, and Evan will sympathize with this, if you say that rather than looking at matching the frequency of one particular mode. Let's just aim to have the same number of modes on average, and we call the modal density. And if you do that for this kind of what's technically called an orthotropic material, there's different properties in these different directions, then a first cut at the answer to that is that the modal density depends on the geometric mean of the long grain and the cross grain stiffness. So you multiply them together and take the square root. And if you plot it on this log scale here, that means they lie exactly halfway in between. So if we take the blue blob and the green blob and we draw a blob that's just halfway in between, then each individual material would have a place in this black dashed line here. That one can make an argument that is probably the least bad version of the criterion, shall we say. That is taking account up to a point in both the long grain and cross grain. So it still slopes down. So this one had a slope of roughly 1, this one had a slope of roughly 3. This one is halfway in between on the log scale, so it has a slope of 2. So
we should take, if we did the Lukey measurement, if we do them across the grain and along and just average those two radiation ratios, that would in principle
average them in as a geometric mean, multiply them together and take the square root, rather than adding them together and divide by 2.
Okay, and could you explain why? Oh, so
yeah.
Or I'll take your word for that. Okay.
Yeah, the answer to that is there's a little bit of mathematics. You can find it in euphonics if you really want to know. And it's still an approximation. Everything in this business is an approximation, but it's the only simple thing that gives you a starting point. Because on average, all the modes use both stiffnesses in a rather balanced way. And the way they combine in the formula for the frequencies and to get this modal density more or less depends on this geometric mean of the two stiffnesses.
And so all things being equal, if you're only measuring along the grain, then if you choose the lightest, you're not going to get the optimal. It would be somewhere in the middle of the range. Is that
possibly
right?
True? And notice there's something that, yes, and you don't usually use balsa. You usually use spruce, which is actually somewhat in the middle of the range. And perhaps that's the reason. Although it's still the case that the black dashed line, balsa wood is still the most extreme on this combined measure. So that's a definite maybe.
I have a pile more questions, but I'll turn it over to whoever's next.
So the next person in the queue is actually in the chat. So Jesus Torres writes, if we are capable to measure density grain by grain, then one can model a wood plate as a composite gluing several grains, each one with its own properties.
That's a true statement. It's rather a laborious thing to do. Well, yeah, right. You can do that at various levels. You can take the individual annual rings and think of that as a layered composite and have average properties of those, or you can go all the way down to the cell structure level and you can take the geometry of the cell structure and you can compute up to a point the various stiffnesses from that. We have done that. It was reassuring that when that was done, I had a German master student some years ago who wanted a Germanic project to do. And I thought tracing the cells in a scanning electron micrograph picture and mapping that out and coding them all up was a suitable project, which indeed it was. And he was able to take the actual cell structure of a particular piece of spruce, do the right kind of averaging and aggregating over the various motions and get a plausible prediction of all 9 of those stiffnesses, in the same ballpark as published measurements. So you can do that. You can also do things with rings. CT scans won't show you the individual cell structure yet, not quite. The cells are too small, but yeah, you can certainly see the rings and the micro density variations. So yes, Jesus is correct. It's possible in principle, not wonderfully obvious what you can do with the information, because when you look that hard at pieces of wood, you may have noticed in those spruce beam specimens I had earlier that they were all reasonably well on the quarter as an average, but as you went along the length of those beams, you could easily get 10 degrees this way and that way in the annual rings just from the growth variation. And those samples were all from the same tree. Those were the taken from the tops of the set of violins that David Rubio made for us. So he took 6 adjacent pieces from the same split for the backs and the same for the tops, and then the offcuts of those, and still the growth variations were sufficient that you could hardly recognize it as looking the same in the different samples. So it's a complicated story.
All right. George is next.
Okay. I actually had the same question as Joseph, but then I've got two sort of follow-up questions there. I mean, is there a case for making a figure of merit out of the geometric mean of the 2 moduli?
Indeed, yes. No, that's
we are actually starting to lose out as we go to lower and lower density. We're potentially losing out on I mean, it'd be interesting to see the calculations, what the shape of the curve looks like. But if you actually
it looks like that black dashed line that I was showing a minute ago. So it's
somewhere
still
in between the two.
It's still in the same order, but yes, you get a misleading impression by only looking at long grain stiffness. And the question you're usually asking is actually not, shall I make this one out of balsa wood? You're saying, shall I use this piece of spruce or that piece of spruce, which are very similar in absolute sense. So how well the criterion holds up at the fine-grained level of actual material selection is quite a moot question. And of course, in your actual instrument, your actual plate, the cross-grain stiffness that you need is not the one that would be the case if the piece of wood were perfectly quartered. It's whatever you've got and that the timber yard has given you by the time you've carved it out, which might be off by this 10 degrees, and so you've lost a factor of 2. So it's the actual value, and then it'll vary over the profile of your arch as well. So it gets very messy very quickly.
I mean, the other part of the question really is that it seems to be a fundamental part of the design concept of a violin that is stiff along the grain and not across. So the question then is like, how much do you want that cross grain stiffness to go down? I mean, in the case of, say, the bass maker Vincenzo Panormo, he sometimes quite often used fir instead of spruce, and in one case pitch pine, but in many cases the middle 2 is made out of 4-piece tops instead of 2. The middle pieces are very often cut at 45 degrees, so they're deliberately, I mean, deliberately made to be low crosswise stiffness. And they're as basses, they're notable for having very, very sort of deep sound, but not a great soloist instrument. So they don't have the brilliance to project, but they do have they do the low frequencies very well. So I mean that's so it's really quite unclear what we should be selecting for in that respect.
That's the only message I wanted to convey, is that it is unclear, it is complicated. Do not take that criterion that people tend to use as the end of a story. It's the beginning of a story. All the things you say are quite right.
But a good start might be to use the geometric mean of the 2,
Yes.
and that would be a steeper gradient than the long
Yeah,
grains.
that's right. It'll be different. And there's also an argument for factoring damping in as well, if you really want loudness. So there's another version of the criterion which involves the damping of the two directions as well. Because if
Okay.
you're, yeah.
Well, it's something to think about and to develop in the future. We're not right there yet, but it's
Yeah.
something technique to polish, perhaps. Okay.
Thank you.
Sean?
Thanks, Fan. Thanks, Jim. Jim, I just had a question about one of your slides. I think roughly 5 or 6. There was an image that I didn't quite understand. I was wondering if you could just go back to that briefly.
Yes, going back is easy. Once I press enough buttons. So 5 or 6. So let's start.
Oh, I guess it was a little farther than that. It was one of the last of the micrographs, where there was I think you said something about a right angle cut, and there was kind of an
This
end
one?
grains. No, okay, and there was an end grain surface, and then above it there was this smooth. Yeah, this
Oh,
one.
this
I
one.
didn't.
This one.
I didn't understand what was going on here. Like, which-
Okay. Yes. Yeah. Okay. This is. So it's a scraped surface of actually let me hold it up. Let me just quit for the moment and hold up. It's the view that the camera is now showing you. You're seeing the end grain at the bottom and the top surface running away from you.
Mhm.
Oh,
Yeah.
okay.
So you're seeing the cell structure in the end grain, and you're seeing the outer surface of the plate.
Oh, okay.
So
So that border is actually a 90-degree angle between the
yeah,
top and the bottom.
Oh, okay.
It's for technical reasons actually. Actually, it's not quite a 90-degree angle. It's easier to do clean cuts on end grain with a slanting cut. So it's probably a 60-degree angle rather than a 90-degree angle. But yes, you can think of it. This is the outer surface of your plate,
Mhm.
and this is through the thickness, and it might as well be a 90-degree cut. Yeah, does that make sense now?
Yep. Thanks.
Right, good.
Don? Hello, Don?
There, am I audible?
Yeah.
Yes, you are audible.
Okay. One thing on trying to get louder by going to higher and higher radiation ratio, I don't think it's been emphasized that you're getting at loudness by a lower impedance. That the normal calculation is with a constant force, you will get louder and louder with lower density wood. But a bowed instrument is not constant force. You know, it's not free, that you have to put that in. So as you go to louder and louder, you're going to have to bow faster and faster to get that thing to make noise. So there's player involvement involved in that, not just plain loudness. The playability of the instrument changes.
Absolutely. No, I think there are two different things in there. Yes, it will feel different under the bow. And the other aspect of changing the body impedance is that wolf notes are likely to become more of a problem. So there are two different aspects of playability that would come in, and I completely agree with you on that.
Okay, the other thing, I came in a little late, maybe you mentioned it, but Jim Ham brought up something with rays, and it seemed that there was some uncertainty about stiffness in the tangential and radial direction. And I don't know if you had mentioned earlier that the radial direction, the cell walls line up much, much better than in the tangential direction, which is why the radial
Indeed.
direction is stiffer.
Yeah, no, you're absolutely right. No, I had the picture of that, but I didn't really say much about the tangential direction at all. But you're absolutely right. Yes, I mean, shall I show? Shall I put the slide back? That you're spot on with that remark. Where's a good picture for that? We want one of these.
Yeah, there's often a misconception that the thick
Look at this picture
grain
here.
line, the thick grain lines are like beams, except that's the weak direction.
Yeah, no, you're absolutely right. So here's a ray cutting through. So this is the radial direction. This is the tangential direction. And exactly as you say, the cells are rather nicely lined up in the radial direction because that's how the tree grows. Each cell reproduces into another one next to it, whereas they're randomly staggered like brickwork. Well, rather random brickwork in the tangential direction. And if you think of squashing in that direction, bending the cell walls, it's easier to bend these things that are in the middle. So no, absolutely, you're right that the alignment in the radial direction makes that one a little stiffer than the cross direction. And that is the main factor, rather than the rays. If there was a higher density of rays, the rays also take you in the same direction. And the main influence of the rays is not their actual substance, but here's a ray cutting through. Of course, that just because it's there, it makes this alignment more precise. So this bit of the cell walls of the tracheids are really lined up rather nicely. So they're stiffer, so that bit. These ones far from the rays are easier to bend. So yes, the rays do have a stiffening effect, but they do it because of this alignment effect mainly, rather than just by being there and like reinforcing rods. So,
any other questions, Don?
Next. I'm done.
Okay, Tom?
Hi.
Hi.
I have a question about, well, I spend a fair amount of time when I'm selecting wood for an instrument, scratching my head as to how this one piece of spruce is going to interact with a piece of maple. And I wonder if you might talk a little bit about how different properties of these woods come together in an instrument.
That's a great question, and I don't think I have anything useful to say about it. That's a hard question. The only criteria we have are things like this super crude radiation ratio criterion, which usually only thinks about the top and only thinks about makes these sweeping assumptions. To do a calculation like that, taking account of more of the complication of the box, it's not even obvious to me where one would begin, because, I think that's absolutely it's your job to worry about that. It's too hard, too hard for me at the moment. That question. There are no. I can guarantee that there are no simple answers to that question. I mean, even if you just had a Sabar type cigar box fiddle, it would still be hard to say anything very much about what the backplate does.
I've had a couple of instruments that I made out of some old lightweight maple that was quite stiff, and tried to pick a very reasonable piece of spruce to match, but I found challenges with those instruments in particular, the light, stiff maple. Now maybe it's a little off the charts as far as best choice, but beautiful wood is hard to turn away.
I think for that, the person who knows, well, the people here who know most about that kind of question are George Stepani and the other people who were involved in that Bilbao project, because they tried to do just exactly that, make instruments with different tops and different backs and matching stiff with stiff or stiff with floppy and so on. And so I don't know if you heard Georgie's, but there have been some First Friday's talks about that data, and it's nothing is super clear. But if you didn't catch those talks at the time, those recordings are well worth listening to. Let me just feed in something else, something I have often wondered, and I wonder if anyone's ever actually tried it, is what happens? Why don't we make the back also out of spruce? What would happen if you had a violin that was more symmetrical, so that, you know, two tops apart from the F holes and bass bar? Would it be a disaster? Which direction would that take you in? I simply don't know, and it seems an interesting question.
I tried it. And it was a disaster, but it was so long ago that I don't remember why. But this is a super interesting question, because I've made quite a few backs with aspen or poplar, and some of them have densities absolutely where spruce is. And I've made excellent violins with, by my own standards, using, backs that were really very light, and their tap tones were correspondingly very high because they left them rather thick, but it didn't seem to change anything in the overall shape of the spectrum. It was just, and I've also made really good violins with rather heavy backs. So my conclusion is, I don't think one's trying to match the top and back. It's just two variables, and the back has a much smaller effect in my experience to the measurements anyway. But it might be an interesting thing to do at Oberlin, make a bunch of backs for one violin and swap them out.
Yeah. So,
all right. Jesus, are you connected now?
You're muted, are you? We're not hearing you. Oh, no,
Yeah.
you're not muted, but you're not audible.
Nope,
No.
we cannot hear you.
We're not. Mute and unmute, just in case that does it.
Or you can just type a thing in the chat, perhaps. I think maybe that's what this meant.
Yeah, it says, you show us a quick way to estimate both Young's modulus by means of density. Is there something like that to estimate shear modulus?
Good question. I'd have to look that up. Sorry, I'll be back. I'm just looking on my bookshelf. Yeah. So the book I would have to look in is this one here. Yeah, you probably can't read the authors' names, but Mike Ashby is one of the authors of this. Mike Ashby is the guru of that kind of question of systematic material choice for design. In the small print of the slides, those log plots of property things are known as Ashby maps. One of the things he wrote jointly with Lorna Gibson was this book about cellular solids, foams and honeycombs and all of that. That's where I got this comment out of. They may have an answer to that in there somewhere, but I don't have it at my fingertips right now.
All right. Joseph Najiveri, I'm going to come back to you because we have a couple of questions in the queue that have been sitting around for about 15 minutes. So let's go through this. The questions of the queue, the chat first. So first question, how significant are the effects of ground and varnish on minimizing any of the differences in stiffness and damping properties?
That's a question that doesn't have any short answers. if you use a very lossy varnish, then yes, varnish can have a big effect on damping and usually a relatively small effect on stiffness. So you could, a really thick, soft varnish will make the whole thing more highly damped, and it will tend to reduce the ratio of long grain to cross grain stiffness just because you put a layer on the surface. Then it doesn't make all that much difference to the long grain stiffness because that's already really high, but it will stiffen up the cross grain direction somewhat. But I don't think I have anything short and snappy to say on that question. Yes, it's one of the variables. It's hard to do the measurements. We have tried to do that rectangular spruce plate measurement with varnish at various stages, and then different stages of treatment, and then waiting for time for things to change. And in principle, it was a really good experiment. In practice, it never worked very cleanly because there's something else that happens if you have a spruce plate that's part varnished or fully varnished on one side, and you then keep it on a shelf for 2 years, which is the plate tends to warp this way and that as the humidity changes. And curvature of the plate is a killer for that plate-based vibration measurement, because you make this, it becomes like corrugated iron. The bending in the direction perpendicular to the curve from the humidity effect will get much stiffer, and that's a much bigger effect than any contribution from the varnish. So I don't think there's any really clear data on that.
All right. I skipped over Marty's question. Is wanting high loudness the opposite of wanting high modal density?
It's not the opposite. It's more orthogonal than the opposite. They're two different ingredients that you can inject in. Yes, I mean the usual calculation is to maximize loudness while keeping the modal density fixed. But there's a simple formula for you could do variations on that criterion with any mixture of those things. I don't know the answer off the top of my head, but I don't think they're opposites. I think they're different axes in the in some space somewhere, and you could mix and match them in different ways if you had a reason for wanting to do any of those things. But
all right, have a question from Steve McCann. I have noticed that the cross-grain stiffness of Engelmann spruce, a less dense wood, varies considerably with the width of the annual rings, whereas with American red spruce, a much stiffer and more dense wood, the cross-grain stiffness varies less with the spacing of the annual rings. Any explanation?
I think that sounds plausible. I mean, the denser the wood, the thicker the walls, and the higher the cross-grain stiffness is going to be. And it becomes, I mean, this argument that the cross-grain stiffness is governed by cell wall bending really works for the thin-walled cells in the spring growth. It doesn't work for the thick cells in the late growth. The denser the wood, on average, the thicker those walls are, and the less clear cut the effect is. But it will the cross-grain stiffness is going to be higher, probably anyway, for those denser materials. Well, a lot higher because of that cube law, I guess. That's yeah. So maybe the trend line that I had for the different timbers is already going in the direction of that comment. Does that make sense?
All right, let's go back to Joseph Najiveri.
You're
Unmute
muted.
yourself.
So in your discussion, you haven't mentioned that the spruce tree has a rather thick layer of sapwood outside that can vary depending on the size of the tree, 4 to 6 centimeters. So when you talk about cross-grain stiffness, then you go through from the outside towards the center, you go through thin walls, sapwood cells, and the more you penetrate to the inside, the cell walls get thicker and thicker. So I would think that the cross-grain stiffness actually should vary along the radius, and shouldn't be considered as an average value. Did I express myself clear enough?
Yeah, certainly sapwood is chemically different from heartwood, but in the end, as the tree continues to grow, the heartwood is made out of old sapwood. So the cell pattern, I mean, right near the core of the tree, when it was just a little sapling, I dare say the cell structure might be quite different. But once the tree is getting going, it's just adding a new layer of cells and a new layer of cells on the outside. And those start out as sapwood, but turn into heartwood as they get absorbed into the tree. So I think the cell geometry, except when you're really near the middle, is roughly the same in the heartwood and the sapwood, but the chemistry is different.
Well, the thickness of the cell walls is quite different. The density is significantly different. There must be a reason why the great makers try to maximize the amount of sapwood they built into their instruments. You can see many of the Guarneri and Stradivari instruments, the entire central region between the F-holes is made of sapwood. Okay. So I would expect, it would have a major effect on damping. I expect the sapwood damping to be much less than the damping of the heartwood. So I wonder, excuse me, I wonder if you have any opinion about building violins with more sapwood or less sapwood.
Yeah, it's an interesting point, and I have no data at all. I don't think I've ever seen any measurements. I mean, I would want some data first, and I don't think I've seen any measurements on the characteristic difference of sapwood, because the wood still needs to be thoroughly dried and seasoned, whereupon the difference in the heartwood and sapwood is somewhat reduced, I suppose. But I'm just guessing. I've not seen any data, and it's an interesting observation that you described. So now there could well be a project there for someone to pick up and look at.
Well, I think many people know that sapwood stains differently from the heartwood, which means also if you soak the wood with a salt or acid or anything, the sapwood picks up more of it within the cellular walls than the heartwood. So the differences of the chemical makeup can be the basis of useful manipulations, let me put it that way. I don't know if anyone has any experiments done in this regard.
Could I add something in there? If you're doing speed of sound measurements, the speed of sound gets faster toward the center of the tree, the density gets greater. So I think one uses towards the outside of the tree, well, the grains are finer and it is a bit lighter. Who knows what the old Italians did. So my question to you would be, it sounds from what Jim was saying made sense that the sapwood is gradually converted. Is that a gradient, or do the outer 3 centimeters? I mean, is it? I don't know how to express that clearly. How far in can you call it sapwood? Does it all stay light and then it starts getting denser? Is there some sharp division?
Frankly, it seems that the division is quite sharp, because if you stain a plate which goes from the outside all the way to the inside, you can see clearly a very strong staining at a line which is like 4 to 6 centimeters from the bark. And then the staining is much less.
I would expect that to be the result of these border pits not having fully closed. That's the thing that makes the wood more or less porous, is whether these membranes in these bordered pits have sealed. So fully lignified and dry heartwood, those are closed. So indeed, you can't soak anything much into the wood very easily unless you do the bacterial degradation thing to eat those membranes.
Well, that would make perfect sense, because if the sapwood is for transmitting the sap up, you wouldn't want it leaking into the center. So, and presumably we need a certain width of sapwood. And so, yeah, so I think what you say, Joseph, makes perfect sense. But of course, it must be converted eventually into regular wood.
But the difference between the sapwood behavior and heartwood behavior is important for the maker, because all of us put ground into the wood. Some of us put salts into the wood, and these chemicals are absorbed differently by the sapwood than by the heartwood.
Well, have you measured a difference in damping in between sapwood and other wood?
I don't measure anything.
Okay.
I work on violins because violin making is fun. Doing scientific experiments for me is not fun. So I hope you appreciate that.
Yes, very much.
I do chemical science for other reasons, for the origin of life, but violin making for me should be fun.
Fair enough.
All right. Colin.
You're still muted.
I don't think I
No,
am.
you're okay now.
There you are.
No, I'm just being a bit slow. Wonderful talk, Jim, as always. Do you think there is an argument for different criteria on the choice of woods and damping and things like that for performance at high frequencies and compared to low frequencies in the signature mode region? In the high frequency range, the modal density is obviously very important. And what is your view about damping in that area? Because the sort of theoretical argument is, of course, that the amount of, as you go through a resonance, it becomes independent of the damping, as I understand it. So is damping important, is a question, in the high frequency range of the violin?
It's once the modal overlap, this may degenerate into a technical discussion.
I don't want it to do that.
No, Evan will know the answer to this. Maybe we have this discussion offline. There aren't any simple answers. Once the modal overlap is large, then indeed the fluctuations you see in any frequency response are no longer associated with individual modes, and indeed they don't depend very much on the damping. It's all to do with phase relations of things when there's many modes. And the extreme example of that is room acoustics, when the modal overlap can be huge. And everything about room acoustics is statistics rather than deterministic calculations. But
So-
we don't get that high in instruments.
But yeah, right. But in the signature mode region, the damping is going to be largely dependent on the sharpness of the resonances, and well away from the resonances themselves, the damping is not important. So how important really is damping in the signature mode region?
It governs how high the peaks are, and it governs wolfiness. That's
Yeah.
a clear-cut thing. It would it still makes the peaks higher and the dips lower. That has the potential to come through in unevenness, which could be a bad thing, and in added sensitivity to vibrato, which could be a good thing.
Yeah.
So it's having an influence on both of those. It's easy to believe that both of those matters, and they go in opposite directions. So the maker must be striking a compromise somehow between those things. The easiest way to investigate those kind of questions is the sort of project that Claudia did when she was here, when you played her the virtual violin. There you could wind the damping up and down while playing the instrument, and that's something you can never ever do in a real fiddle. It's not entirely true that damping only matters near the resonances, because the anti-resonances get deeper when damping is lower, as well as the peaks getting higher. So it does have some. It changes the peak to valley height across the range in the low frequency region.
And may I make one more comment? I mean, when I was doing my earlier finite element computations on the violin, my software wasn't sufficient to deal with orthotropic material. And so I had to go, I found various ways to get around that. But working, in fact, with the geometric mean of the two, cross grain and long grain things, gave measurements that were absolutely consistent with what one actually observed in measurements. So I concur with the comment about the importance, in fact, of both measurements really, and really the geometric mean is the obvious thing to take.
Yeah, I mean, you're right. It's an approximation, but it is the obvious approximation. It's in Kramer's book, so he was well aware of that one.
But the interesting thing is it works well for the low frequency modes as well as the high frequency modes.
Indeed, yes.
Okay, thank you, Colin. Jeffrey.
I had posted a question in the chat about, can anyone discuss characteristics between or differences between a spruce top and a pine top for an instrument?
That sounds like a maker question. Would anyone? I have nothing intelligent to say about that, except I could look up the properties and tell you roughly what it might mean. But
Jeffrey, did you have in mind instruments that are made with some species of pine versus spruce? I mean, and that's known. There's so much variation about what people call woods.
I mean, of course, I only know what I see in front of me and on an instrument, and from my albeit very limited knowledge, I found that people say that it's pine when you see a large shading area off of the winter grains, and that it's spruce when it's kind of very carefully defined dark light, and I was just wondering if people have anything.
I can add something anecdotal about that. I have here a cello that I recently did sort of major restoration work on it, which is probably a Kennedy cello, the top of which is made of pine, not spruce, very clearly pine. I don't think the top is original to the cello. I think it was a later addition, that, but nevertheless, it's a pine top and it's a very nice sounding cello. Just anecdotal.
Here's another related maker question. Why, except back in the past, I guess there was a cost element involved about why someone would choose a maple back versus a poplar back or some related one.
I think you've answered that. The cost.
Especially, as it happens, we had Robin Aitchison visiting yesterday. He's of course a cello man, and in that he was grumbling mightily about how difficult it was to get good wood big enough for cellos. So in the cello world, there may still be an element of beggars can't be choosers to some extent. It's easier to make that decision on aesthetic or acoustical principles or whatever for violins, because there are more trees that are big enough to give you nice wood in violin size. But the cello makers, he's tried all kinds of things, and it's obviously a serious issue for him, just in terms of wood buying, to get wood of a good quality big enough for cellos, and double basses must have it worse again. So that pragmatic factor must still come in, I think.
Well, of course, one very frequently sees cellos, for instance, go frillers with wings on because they couldn't get a piece that's big enough.
Yeah.
And it basically comes down to how big the wings are, whether it becomes a 4-piece back or a 3-piece back. I know there's at least a couple of Strad cellos that have 3-piece tops because he was experimenting with not having a center seam. Of course, having a really 3-piece top, depending where the seams are, gives you these equivalent of making an instrument that has a sound post crack and a bass bar crack right from the get-go.
Yeah, I don't think I have anything intelligent to add on that question. Good questions. Good questions.
Any other questions from the audience?
Jim, you might just talk about curly wood, what that does to stiffnesses.
It reduces it because of this alignment issue. I mean,
across and along.
Well, it depends where the curls, which direction. I mean, if you map out the cell structure, the huge anisotropy of softwoods is because you've got really strong alignment in the grain direction and much less alignment in the cross direction. If the whole cell structure is waving away, then everything, other things being equal, will be less stiff. But of course, those woods also tend to be denser, so have thicker cell walls. So you've got your maple always, nearly always, is higher density than spruce. Other things being equal, just because there's more stuff in it. And ultimately, waviness wouldn't matter. If there's no airspace left in the wood, then it doesn't matter what, because you've got solid stuff, cellulose and hemicellulose and what have you, I suppose. So it'll be roughly the same in all directions, and will be just like a sort of solid polymer material. Fiber reinforced polymer, I suppose. But as soon as you've got the empty space, that's the key to all these really extreme ratios of stiffnesses, and waviness will always work against that.
So the magic ingredient is air in
good
wood. And with is it the case that hardwoods have shorter fibers, and so that decreases the stiffness along the grain, or is that not relevant?
I don't know off the top of my head. I was dodging around. I'm no botanist. I've told you about the sum total of things that I could look it up, but you could look it up as well.
Fair enough.
All hardwoods, I mean, the softwoods have just 2 cell types. Hardwoods have 6 or 8 or something. So it's not just the same cells organized in a different way, but they are intrinsically more complicated organization with more different kinds of things and these big vessels. And so there's not much work that I'm aware of on following through the structure of hardwoods into what that says about the stiffnesses.
George?
Yeah, I want to go back to Vincenzo Panormo because something has just occurred to me about this. You know, it is said that the reason why he used kind of pine and fir and recycled woods is because of the shortage of supply of woods during the Napoleonic Wars. So they supplied to other makers in England, particularly the London makers. They didn't have access to the stocks. So we found a bass bar on a John Lott, grandfather Lott bass that's got screw holes in it. It's a recycled piece. But if we go back to these, you know, the effect on the transverse stiffness of the higher density wood. So if you're, for supply reasons, you're forced to use rather higher density wood than you might otherwise have chosen, well, then you might choose to put it off the quarter because you improve that ratio of long transverse to longitudinal stiffness. I mean, I'd not thought of that before because I wasn't really particularly aware of that relationship with the density radial stiffness.
I would say that you clearly change the ratio. Whether you improve it,
Well,
it brings in the question about what is good and what is not good. But
he consistently did that on a number of instruments. Seen he used that configuration of the 2 middle pieces of like 45 degrees, and the outer 2 tend to be on the quarter.
Okay.
So it looks like a deliberate choice. I can't be sure. I mean, it could just be that that's the wood that was available. Who knows? But that would make some kind of sense, wouldn't it? So if you're forced to use for higher density wood, stuff that's a bit off the quarter could conceivably be better.
You could make it more like spruce by
Yes.
playing that kind of game. That may be true. Yes.
No. Interesting thought. Anyway, that's just a comment. That's all. Bye.
Okay, so we're closing in on 3 o'clock because I would like to end the formal part of this, and then, but I don't know. Jim, are you free to stick around for a couple of more minutes after?
I'm okay for a little bit, but
okay,
not infinitely much
because
longer.
Jeffrey,
Yeah.
I'm gonna close this section by you know, concentrating on the core subject matter, and we'll get to the other ones, you know, a little after my question, which is, do we have any data on the effects of humidity on stiffness and damping?
There is data. I don't have it at my fingertips. I mean, there's an effect on density directly because you absorb more water, you make it heavier. You can change. No, I don't have the figures at my fingertips. I've seen something. There was something in the Catgut Society some years ago, that Australian maker Rex Thompson. I think he did something.
But qualitatively, I mean, does it reduce stiffness and increase damping, as I would guess?
My guess is the effects on stiffness are probably fairly small. The main effects are on distortion, aren't they? Just because the humidity.
Well, yeah. So the reason I asked because I think there's a general consensus amongst players on qualitatively which direction humidity, how it affects instruments. And I'm not talking about for better or for worse, but in terms of its playing characteristics, I think there's a definite consensus.
Okay. Yes.
And so what is that caused by? And I've always thought that that's one of the experiments we can do that's relatively controlled, because it's on the same instrument and you just change the humidity, put it into a humidity chamber.
Yeah, I mean, it's not, you have to be patient. That's
Mhm.
the one thing I remember from those. I'd have to reread the stuff. I think it was Rex Thompson. There's some stuff in the old catgut journals. There's an asymmetry in the rate, and I forget which way round it is, but moisture
right.
goes in much quicker than it comes out, or maybe it's the opposite way around, but in terms of 10 times slower or something. I mean, I seem to remember he was suggesting there was a big asymmetry, and you have to be really patient with those humidity. I mean, just putting it overnight in a plastic bag with some
Right.
water, and then
Mhm.
overnight in a plastic bag with some silica gel, you're not getting back to where you started, because the water take up is asymmetric. But there
All
is some
right.
data out there.